This video explains how PostgreSQL works at a depth relevant for backend developers. To understand PostgreSQL, we need to start with how computers execute programs. Modern CPUs contain multiple cores. Each core can execute instructions independently. Each core can work on one process at a time. This is the fundamental execution model. You can run more processes than you have cores. The operating system makes this possible through context switching. Context switching allows cores to alternate between processes. Think of two chefs rotating between 4 dishes. Each rotation has overhead. The operating system must save where one process left off and load the next process state. So what exactly is a process? A process is a running program. It has machine instructions the CPU can execute. It has memory allocated by the operating system. When you compile C++ code into a binary and run it, the OS allocates memory. The CPU begins executing instructions. Every process gets its own isolated memory region, protected by the operating system. Process A cannot access Process B memory. This isolation is fundamental to system stability. Every variable your program uses consumes memory. The stack holds local variables and function calls. The heap holds dynamically allocated objects. Memory leaks happen when you allocate heap memory but never free it. Stack overflow occurs when function calls exceed stack space. Both exhaust your memory region. CPUs have cores that execute processes. Each process has an isolated memory region. This is the foundation. Now let us examine how PostgreSQL uses this model. PostgreSQL starts as a single process called the postmaster. This is the parent process that manages everything. When a client connects via TCP, the postmaster creates a dedicated child process for that connection. One connection equals one child process. Each client connection gets its own dedicated child process. This is a core design decision in PostgreSQL. Why does PostgreSQL use multiple processes instead of multiple threads? With threads, you have one process with multiple threads sharing a heap. Memory efficient, but one thread crash kills the entire process. With multiple processes, each has isolated memory. If one crashes, others continue running. This costs more memory but provides fault isolation. PostgreSQL chose the multi-process model when designed in the 1980s and 1990s. It has kept this architecture. If one client connection crashes, others remain unaffected. Stability over memory efficiency. Despite having separate processes, PostgreSQL uses shared memory for coordination. The lock table tracks which rows are currently locked. The buffer cache holds frequently accessed data to reduce disk I/O. Creating TCP connections is expensive. Connection pooling maintains open connections that can be reused. This avoids repeated handshake overhead. Different languages handle concurrency differently. Node runs one process with one thread using an event loop. Python can use multiple processes or threads, often configured through frameworks like Uvicorn. In a real system, each application maintains a connection pool. Each pooled connection corresponds to one PostgreSQL child process. PostgreSQL max connections setting limits how many children can exist. Beyond that limit, new connection attempts are rejected. You end up with many processes. The operating system schedules them across available CPU cores using context switching. When running on the same machine, communication uses the loopback interface. Over a network, standard TCP/IP applies. Both use sockets and ports. PostgreSQL is a multi-process database. Each connection gets a dedicated child process. Processes coordinate through shared memory. The operating system handles scheduling across cores. That covers how PostgreSQL works.